My name is Zach Gamache, and this is my demonstration project for MAE 535, Design of Electromechanical Systems. I will be demonstrating Ampere's law by running electrical current through a wire and moving small permanent magnets. Ampere's law is a way of calculating the magnetic field from the electrical current running through a wire. I will create a magnetic field from a straight wire along with a solenoid. My first example, I will show how a straight wire can create a magnetic field. Magnetic field is equal to the current divided by 2 pi r, where r is the distance from the wire. For this example, I have a 6-inch copper wire, a small spherical permanent magnet, and a 6-volt power supply consisting of 4 AAA batteries. So I'll start with a permanent magnet at a large distance away, and I will hook up the power supply. And the permanent magnet does not move. I will go ahead and place the permanent magnet closer, so I'm reducing R in the equation, and then I will hook up the power supply, and you see that it starts to move away slowly. For the last one, I will go ahead and move this permanent magnet all the way up to next to the wire, making R even smaller, and I will hook up the power supply. And you see that it moves away. So the magnetic field is related to the current divided by 2 pi r. As r gets smaller, the magnetic field gets bigger. For this example, I have 2 wraps of coils, one containing 5 turns and one containing 15 turns. I also have a small magnet cylinder in shape. The magnetic field is equal to the number of turns times the current divided by the length of the solenoid. So I will put the magnet on its side in the center of the 5-turn solenoid, and I will hook up a power supply. And what you see is a little bit of movement from the magnet. I will go ahead and put the cylinder magnet inside the wire with 15 turns and attach the power supply. And what you see is that the permanent magnet falls on its side. So as you increase the number of turns, you increase the magnetic field. And in this case, you're able to knock the magnet on its side. For this example, I have a solenoid that consists of 50 turns and 7 permanent magnets wrapped in a row. I will put the permanent magnets inside the solenoid and apply current. What you see is the permanent magnets enter the solenoid, current comes in the front here, and by the right-hand rule the magnetic field is going down the center. Now I will start the permanent magnets and I will switch the entrance of current, hook up the power supply. What you see is the permanent magnets get forced out. Since current enters on this side, the magnetic field is going through the solenoid and forces the permanent magnets out. For my last example, I will use the same solenoid of 50 turns, and in this case I will use 15 permanent magnets aligned in a row. I will put these 15 magnets in the center of the solenoid and apply current. And what you see is that the permanent magnets entered the solenoid. I will now redo with a solenoid of 10 turns. It's the same 22 gauge copper wire wrapped around a toilet paper tube. I'll use the same 15 magnets, put it inside the center of the solenoid and apply current. And what you see is the magnetic field is not large enough to move these permanent magnets. I will go ahead and remove 5 from this line and place on the center of the solenoid and apply current. And what you see is now the magnets were able to enter the solenoid. So this shows that the greater the number of turns, the stronger the magnetic field.